Hello, I'm H.Y. Today I will share about this paper called Robust Gas Demand Forecasting with Conformal Prediction. And this is an applied paper about the conformal prediction. And this is come from this one. It's a French researcher to do this paper. Okay, let's start. So today I will talk about the introduction and the motivation of this paper, and talking about uncertainty quantification with prediction intervals, and the conformal prediction methods they used, and the main part is their experiment. Okay, so with several sources of production and multiple customers of industrial gases across France, it is the company's responsibilities to guarantee the availability of supply. That means we should know when to deliver the right product to all its customers on time. So by taking into account geographical and logistical factors, managing the customer's product storage has an effect on the whole supply chain from production to distribution. And dispatchers need to estimate the future trends of customers' demands in advance based on their years of experience in the field. So in order to help the dispatchers in their estimations, multiple forecasting algorithms have been proposed to predict the needs in production as precisely as possible in the short term, and compare them with the dispatcher's estimations. Even the best forecast model can suffer from uncertainty between the forecast prediction and the dispatcher estimations. So we shift to focus on quantifying the uncertainty associated with the forecast predictors. So obviously, these intervals should have a high coverage probability to be used in production with great trust, while also being as narrow as possible to be informative for the dispatchers. So conformal prediction will produce prediction intervals backed by theoretical guarantees while being able to be applied atop any regression algorithm. So, and the next part talking about uncertainty quantification with prediction intervals. So we're just talking about this concept about it. So we let xy is in a probability distribution pxy, with x be the random vector of features and y be the target in learning text, and alpha be the miscoverage level, and the prediction interval obtained via algorithm C alpha x, it should be contain a true value of the random variables y, and in 1 minus alpha times 100% of the time. So ideally, the probability of y belongs to C alpha x given by x is equal to y minus alpha. It holds the true conditionally on the value taken by x. And this statement is said to produce conditionally valid intervals. This is the most ideal case, but if we have a weaker condition for the probability y belongs to C alpha x equals to y minus alpha, and then this procedure is marginally valid. Okay, so we have two main approaches to build the interval. C hat alpha x with the lower bound y hat L and upper bound y hat U. So the first matrix is we have two main approaches. One is we can add an error margin, delta alpha, to the point prediction. Like the f hat x minus delta, and the upper bound will be f hat x plus delta. And the f hat will be estimated conditional expected value. And the delta depends on the data and probabilistic statement made with the prediction interval procedure. This is the first one. And the second approach is we can use the bounds directly, like quantile regression. Like the lower bound will be q hat alpha low x, and the upper bound will be q hat y minus alpha high x. And the q hat beta is an estimation of a conditional quantile, and with the alpha low plus alpha high equals to alpha. And we have the two main metrics for this uncertainty qualification. So we let n be a number of samples in test data, and the miscoverage level alpha, and so we get the corresponding nominal target coverage as 1 minus alpha. So the first one will be prediction interval coverage probability. They call this PICP. Yeah. And this is we call the coverage we discussed before. And another metric is called the average length, which is the average of the upper bound minus lower bound. Yeah, and sometimes we just want to show the average length more convenient, so we just normalize the average width to comparison over different data sets. So we'll do it that. We'll do it that the sum of the upper bound minus lower bound divided by n times r. This r is equal to the maximum of the y minus minimum of the y. Okay, so after we're talking about the uncertainty qualification, so we can talk about the conformal prediction. So the conformal prediction is a set of the distribution-free, model agnostic, and non-asymptotic methods to do uncertainty qualification by constructing valid prediction sets or intervals. So the probability coverage is backed by theoretical guarantees. So given the miscoverage probability alpha, this is a set of exchangeable training data so given a miscoverage probability alpha and a set of exchangeable training data and a test point with common distribution pxy. So the conformal prediction procedure builds the prediction sets so that the probability of the test point y belongs to the C alpha will be larger or equal to 1 minus alpha. So over many calibration and test sets, the C alpha x will contain the absolute value of y with frequency of at least 100 times y minus alpha percentage. So the first and the most common conformal methods is called the split conformal prediction procedure. And here's the step for the split conformal methods. So first we need to choose the base prediction model, and we choose the non-conformity score. Usually it will be y minus the absolute value of y minus f hat x. And the third one we'll split the data to two partitions. The first will be fit subsets and celebration subsets. And we compute the prediction model from the fit subsets, and we got the scores, non-conformity scores from the celebration sets. And we'll get the error margin delta alpha from the empirical quantile of the R. So we can build the conformal prediction interval for the observation of the new test data. So this is the split conformal prediction. And also the locally adaptive conformal prediction, mostly this is similar to the split conformal, but the main difference is they use the scale scores. Scale scores will be, I just talk about the absolute value of yi minus f hat xi divided by sigma hat x. So the sigma hat x is a predictor of dispersion learned on training data. So in this paper, the sigma hat will predict the conditional mean absolute deviation condition on x. So the prediction interval will be f hat plus or minus the sigma hat times the delta alpha, and this delta alpha, this is scaled up by the sigma hat. So this is the locally adaptive conformal prediction. And another one it is very common to use is the conformalized quantile regression. We also call this CQR. And this gives the nonconformity score, which is we choose the maximum between the Q hat alpha low minus yi and the yi minus Q hat y minus alpha high between from a number of the distribution sets. And the prediction interval of the CQR is given by the lower bound be Q hat alpha low minus delta alpha, and the upper bound will be Q hat 1 minus alpha high plus the delta alpha. And the delta alpha is a correction margin that guarantees the finite sample coverage for the control predictions. Okay, so also we have the jackknife plus. It uses either a leave one out or the k-fold data schemes for a better statistical efficiency. And also when we base the prediction is an ensemble learner using the backing, and we can compute the nonconformity scores via the out-of-bag with a negligible computational overhead. So the jackknife plus after bootstrap and the quantile out-of-bags conformal prediction methods are compatible with any point f and interval q predictor. And moreover, some of conformal prediction will focus on the non-exchangeable data, like the time series. So this literature will introduce additional assumptions on the problem to get close to the properties of conformal prediction. So there are some examples, like the first one is Gibbs and Candace, which I talked about before, and Zephyrin. They work on the obtaining adaptive miscoverage probabilities alpha for online CP. And the Di Giovanni, he works with the multivariate functional time series applied to demand prediction in the Italian gas market. And in this paper, they also introduced this method called ensemble batch prediction interval algorithm. This is a modification of the jackknife plus after bootstrap that also use OOB to estimate LOO nonconformity scores and aggregate predictors. And this method also avoids overfitting without resources to data splitting, which improves the computational efficiency and yields the constant size intervals. And so from an ensemble batch prediction interval, this paper also extends this methods to the adaptive ensemble batch prediction interval. And use the extension for the local adaptive methods to the ensemble batch prediction interval. So this data is also supposed to be generated by the model yt equals to fxt plus the epsilon t. And the function f is unknown, and the errors are identically distributed but not necessarily independent. And the most important, the d-dimensional feature vector xt, it can include the history yt plus t minus 1, yt minus 2, blah, 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 of the yt, such as both traditional time series models and complex machine learning techniques are eligible. So this is the algorithm. Just let me. Okay. So the input will be a training data and the point prediction algorithm, and variability prediction algorithm, and miscology level, regression function, and number of bootstrap models, batch size, and test data. And here yt is revealed only after the batch of pi with t in the batch are construct. So, okay, so first we do the bootstrap. So sample with replacement index and index set SB from indices. So we compute the f hat and the sigma hat with bootstrap. Okay, so and the next part will do the LOO. So we'll get the for each data in the for each training data, we can get the f hat minus I and sigma hat minus I from the aggregated data from these bootstrap. And we can get the epsilon hat I. This epsilon hat I is computed from the locally adaptive methods. Okay, and then we get we do that we for all the test we do all the test data, and we'll get the and for first we'll find the quantile. Okay, we'll get the quantile, and quantile of f hat minus t. Okay, and we'll compute the sigma hat minus t, and we'll get omega, which is the 1 minus alpha quantile of the epsilon. So so we can get the a prediction interval. Okay. And the next part is experiment. So in this experiment, the customer demands forecasting dataset was to be shared among the contributors of the on this website. will contain sensitive customers' data. And the dataset includes data related to the historical consumption of industrial gas across 7 years, customers and order specifics, geographical distribution, and seasoning parameters. And we have the 29 parameters combination from source, product, and customer categories. And we obtain a unique time series of gas delivery. And we aggregate product quantities weekly, and the objective is to predict the accurate prediction for the following week. And we approximately 350 weekly quantities per time series. The dataset is composed of around 10,000 observations in total. And the forecast algorithm is sliding window leverage the last 4 weeks of data to predict the quantities for the next one. Okay, so they use the 4 models. First is extreme gradient boosting, XGB, and a gradient boosting quantile regression, and quantile random forest and random forest mean variance. And also during these learning phases, the parameters of each model obtained through the minimization of loss functions. And for the XGB and the random forest and quantile random forest, this will be the squared arrow. And the gradient boosting quantile regression will be the pinball loss. Okay. And also they use the following conformal methods. First is split conformal, and second will be locally adaptive conformal prediction. And CQR, ensemble batch prediction interval, and the next one, the adaptive ensemble batch prediction interval. And also, and we set out the sequential cross-validation scheme with five data sets. And the first data set covers the first 3 years of data. And the second one includes the first 4 years of data, and so on. So the third one will be use the first 5 years, and the fourth one will be the 6 years, and the last one will be the 7 years. And each training data set is split to the feed and celebration sets according to training sets will be 80%, and the celebration sets will be 20%. And the final year of each data will be used as test sets. Okay. So this will be the methods they use. So for the extreme gradient boosting, they use the split conformal and the ensemble batch prediction interval. And gradient quantile regression, they use this two, and quantile random forest use this two, and random forest use this three. So we can find the conformalization on this. On this 1, 2, 3, 4. And we can obtain a better coverage in the range 87.5 to 89.2. It's very closer to the target coverage. And also for the conformal predictor approaches based on the mean predictor, we observe coverage is also close to target coverage of 90%. And also for the uncertainty quantitative approaches without conformalization, and the coverage will be lower. It's around 81% to 85%. Also for the average length, so we can find the extreme gradient boost for SCP and enable batch they also have the worse results, especially for the split conformal. This is the worst one, and the ensemble batch will be a little better. And the other conformalized approaches, they produce adaptive prediction intervals with a similar average length performance. And between this one and this guy produced the narrowest adaptive prediction intervals for a slightly lower marginal coverage than other conformal prediction approaches. This one is the random forest adaptive ensemble batch prediction interval. Very long name, huh? So this is the results. This is the results we are just talking about. Okay, and also we choose this this 4, and we just see in five different data sets, because we do the cross validation, so we just check the 5 data sets, and we can find the XGB. The XGB is it is not adaptive, and the other 3 are adaptive. I think this one is the second one, the gradient boost quantile. Gradient boost quantile regression for CQR. I think its average length is larger. I think the reason is they do 2 times of the quantile regression. And this 2 seems better, right? Especially, I think the last one is especially better, the best one. And okay, so just I talk about the extreme gradient boost. It shows the constant size prediction interval is non-adaptive, and the other 3 they have adaptivity with narrow prediction intervals for a series with low variability. And also the gradient boost quantile regression with CQR methods shows the larger prediction intervals than other 2 approaches. So we can see these 2. I think this 2 is the best one, especially this one. Because they just mentioned this method. It has the good coverage, and also it has the shortest average length. So I think this one will be the best methods. Also, the last thing we like to observe is because in industrial operations, we can be interested in coverage related to contextual information that have the operational interest. So we cluster the 29 series into 3 sets. So the first one will be low variable. They have the 10 features whose standard deviation between very small to 0.2, and the mid variation have the 9 series with standard deviation between 0.2 to 0.38, and the high variation for the 10 series with standard deviation between 0.38 to 1. And we can see the contextual coverage shows under coverage with high variance and over coverage with low variance. So here's the results. So we can see the high variance. They have a larger average depth and the lower coverage, and this is obviously under coverage, and 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 then we can find the low variable will be a higher coverage and the lower average length. This is absolutely over coverage. And another thing we can see is like the extreme gradient boost with ensemble batch its prediction is average length is non-adaptive. So the low variable, mid variable, and high variable, all the average length are the same, but we still can see the coverage. The high variable is still lower, and the low variable is still over coverage. Okay, this is today's sharing, and thank you very much, and see you next time. Bye.